Again, my name is Phil Nash. I'm a developer advocate at DataStax. DataStax is building like a platform for generative AI. I'm not here to talk about generative AI today, but that's what we're going for. We've got vector stores. We just bought a company called Langflow, which allows you to do visual representations of building generative AI stuff. And I know there's a lot of talk about that over the course of this conference. So check out things for DataStax as well. Myself, I come from Melbourne, Australia. It's a long way, but the jet lag is not as bad as going to Europe or the US, so that's wonderful. If you ever want to find me online, I'm on Twitter, LinkedIn, Mastodon, whatever your social network of choice is right now. Pretty much as Phil Nash all over the place. So, regular expressions. Why do I want to talk about them? Why do you want to sit here, I guess? I'm assuming that everybody in the room has written a regular expression at one point in their career before. Is that right? Getting nods? Yeah, okay, cool. So my motivation for this talk was very much that I think we all do write regular expressions, but no one ever teaches what can go wrong with them. And the main thing, aside from like writing a wrong regular expression and just selecting the wrong parts out of a piece of text, the thing I mean by wrong and by danger in the title is the regular expression denial of service attack. That is where you write a regular expression that, either due to malicious or accidental intent, you can bring down an entire service. You can bring down a server just through a regular expression. And that's never in those introduction to regular expression tutorials, and I want to scare people with what we can accidentally do with that. I've got some stories about various different regular expressions that have either existed in the wild, have taken down services, and have been kind of leaked into open source libraries as well. It's mostly based on JavaScript, but for the most part, this counts for most languages. I'll cover a couple of things that it doesn't later. But I mostly deal in JavaScript and TypeScript myself, so that is where these examples come from for the most part. I also love this. I've always loved this quote about regular expressions. Some people, when confronted with a problem, think, I know, I'll use regular expressions, and now they have two problems. Now, I always thought, actually, I think this needs to be updated in some respect, because the two problems are, originally the problem you were going to write, the problem you're trying to solve, and the second problem is now you have to write some regular expressions. Actually, there's three problems, and that is this ReDoS, that is this security side of the problem as well. And not only do you have to write the regular expression correctly, you have to do so in a way that you're not going to collapse your own service. And there are two ways that you can break, two ways that regular expressions can break and fall apart and cause you trouble, known as there's both kind of backtracking and then catastrophic backtracking. And we'll cover how each of those kind of work over the course of the next 45 minutes. I've got some regular expressions we'll be seeing as part of this talk. So I hope you kind of look forward to finding out what they all do. I will explain them all as we go along, but these are just all some of my friends who are all very dangerous. I wouldn't use them, but particularly this one. Yeah, that is 3 lines worth. But don't worry, it actually, the problem with this one is just here, so we'll get to that. It's fine. So the first thing I want to talk about is just general backtracking and how that works in regular expressions and the problems that it causes. I've called this section Backtrack Overflow because it kind of centers around a problem that Stack Overflow had at one point that took down the entire of stackoverflow.com. Horrifying experience for everybody involved, I'm sure. That is this regular expression. It was being used. So this regular expression, if I can break it down for you, it comes in 2 parts. We've got the kind of disjunction or operator in the middle there. So the first part, is the start of the string, and then we've got this /s/u200c. So /s is as whitespace character, but /u200c is a Unicode whitespace character that's not covered by /s. So it's all just whitespace. And basically it just means any amount of whitespace, 1 or more whitespace characters at the start of a string, and then after the disjunction it's the same on the other end. So it's 1 or more whitespace characters at the end of a string. It's basically there to help trim off whitespace on a large string. Seems like a reasonable thing to do. Except it's not. It's a bad idea. It's a terrible idea. But to talk about it and use this still looks complicated even after you know what it does. So it's actually easier, I think, to break down regular expressions like this into a simpler form, one that we can kind of talk about more easily. And when I show an example, not use whitespace, because it's real hard to see whitespace on a slide. So this actually can be boiled down to this regular expression. the letter A plus, so one or more times, and then the end of the string. So I've dropped the first part of that regular expression off before the or, just to deal with the last part. And so this is number of A's at the end of a string, one or more A's at the end of a string. And if you test that against a string that has a bunch of A's in it, and then not an A, a B, for example, it starts to show where problems can occur. You see, the way that the JavaScript regular expression engine and many other regular expression engines work is by testing the string until it fails. And then, you start with one character, test the string until it fails, and then you move on to the next character and go on, sort of backtracking back to that. And so what that means is when we test the string in the first place, the JavaScript engine goes, all right, cool. So we've got 5 A's here. And then a B, it's not the end of the, we've got the end of the string, but it's not an A, it's a B, so this fails. All right, cool. Let's go back to the start, move one character on, and test again. And so now we have 4 A's, and we're like, oh, we're nearly there. No, it fails with a B again. Now we can see as humans that this is never going to pass this, because it finishes with a B, we know that. But the engine does not. And so it keeps doing it, it keeps tracking back and moving one step on until it eventually gets a false result. And what you see is, even in the case of what seems like a very simple regular expression here, is actually kind of, well, it takes a linear, the time taken to deal with this expression is both linear in the length of the string, since we have to check all the characters, but then it is times by the length of the string because we have to keep going back and checking again. So it's a quadratic time function, and that's not great. Like, quadratic functions, not too bad if you know kind of the size of your input. But yeah, and 5 A's and a B, not going to take you too long. In fact, I built a little tool which we can test this kind of thing with. Let's get my regular expression there. It was an A, and then a plus, and then the dollar, and then the end. Cool. And if we test A, B, it fails in 2 milliseconds. I don't know if you can see that. Yes, that looks better on there than it looks on my screen. Fails in 2 milliseconds. But if we put a bunch of things in, bunch of A's in there, it eventually starts to take up more and more time, except this browser sometimes caches things like that. Yeah, I'm not going to prove that one with this. Quadratic is not a problem. You see, I'm putting loads of them in there, but it's fine. So if I go back to the slides, what it will show you is that actually the regular expression engine will take 22 steps to actually check all the characters in this in this string with 5 A's. But if you up that to 6 A's, it's 29 steps. If you up it to 7 A's, it's 37 steps. And we can see that actually the increase is more than linear, it is quadratic. And if you take 20,000 A's and then a B, it takes 200 million steps. And that takes time. And that's actually what caused the problem for Stack Overflow. See, what they've done is employed this regular expression to trim off white space on the end of posts. And then a post with 20,000 white space characters in the middle of it, but not a white space character at the end, hit the home page. And the home page gets quite a bit of traffic. And so every single time it was rendering, it did so doing 200 million steps to check this enormous thing, which took a long time for each rendering process, which brought servers down and left Stack Overflow with a 34-minute outage, ultimately. That's quite a long time in terms of the internet. It's quite a lot of time in terms of like nines of uptime. But what I think is even worse about that is that whoever got the alarm, whoever got the page to say Stack Overflow is down, you've got to fix this regular expression, couldn't go and search how to fix the regular expression on Stack Overflow. It's an absolute nightmare. So 34 minutes just because of one regular expression there. And then I'll get to how they fixed it in a minute. But I knew this talk was important because as soon as I'd learned about that and I decided to learn about this kind of ReDoS problem. And then I got an email from Dependabot on GitHub, which was asking to update a dependency in one of my projects on GitHub because there was a regular expression denial of service attack or vulnerability in the HTTP cache semantics module. This is a module that's buried deep in the dependency tree of a bunch of things that deal with HTTP. It was doing a similar thing. We can see the regular expression is appearing up here in this split. That's with it's white space, 0 or more white space characters, and then a comma and 0 or more white space characters. And then it comes down here again just without a comma, it's an equal sign in that case instead. And so what happens here is exactly the same problem. We've got this problem where as long as there's a comma in something, we can then have 20,000 whitespace characters, and it will blow up the CPU. It will blow up the time it takes to deal with this. Same for equals. There they are. I didn't have to point at them. They're highlighted. And so how do you fix it? How do we deal with something like this? Well, first up, limiting the regular expression is probably a good idea. We've got the plus quantifier and the star quantifier that give us 1 or more or 0 or more things. But more can go... screen's gone. I'll keep talking for a sec. Hopefully we can get that back. More characters can go forever, right? 20,000 characters is not a problem for somebody to create accidentally or on purpose in a Stack Overflow post. But you don't probably want to deal with 20,000 characters of whitespace. You should limit what you're actually dealing with there. And so we can either limit the size of the amount of characters we look at in the regular expression, and on the slide it's sort of suggesting limiting to like between 0 and 64 instead of like unlimited numbers. Or you can just limit the size of the string. 20,000 characters is, I don't know, seems like too many probably for your average Stack Overflow post, and they can maybe kind of deal with that a different way. Oh, it's coming back. So we could limit the size of the string. Alternatively, you just avoid regular expressions entirely. You see that whitespace strip off the front or the back of a string? There's a function for that. It's called trim. It would be on the slide right now. There it is. Ah, cool. We're back. You can just use trim. And now Stack Overflow, I think, its backend is written in C#, but I'm fairly sure that C# and .NET have a trim function for their strings as well. So avoiding regular expressions is absolutely a good way to deal with this. If there is a way to do something with a string that doesn't need a regular expression, use that way because it's likely more suited for the job. And so yes, when you decide you want to use regular expression to solve a thing, you now have 2, 3, or maybe more problems. And that's actually what happened in the HTTP cache semantics as well. Oops. In HTTP cache semantics, they stopped using the .* on either side of the comma. They stopped using it on either side of the equals, and instead they trimmed the string there. They trimmed the key there. They trimmed the value there, and they were much happier about the whole thing. And everybody had to update their dependencies. So that's dealing with large strings and large issues with it. Like that might not come up, but do know that you should be limiting the size of those things. But they're the sort of less likely ones to happen because it's just dealing with regular backtracking in a regular expression, and it just runs at a quadratic time. Not too bad for most inputs. It's that like 1 in a billion that hits the front page of your website and takes everything down. Catastrophic backtracking, on the other hand, is the one we really do want to worry about. Catastrophic backtracking ends up in an exponential time to measure with a string, measure a regular expression against a string. And let's see how that works. I'm going to start with Node Fetch on this one, another open source project, the implementation of Fetch from the web API in Node, which is now a little out of date as we have Undici, I think it's called, which is a spec-compatible version. But all to be said, Node Fetch had this little regular expression in it. It's just an expression to say, hey, we're looking at the start of a string, and we have like anything 1 or more times, and then a dot, and that kind of group 0 or more times, and then localhost at the end of the string. So it's a URL that either ends in localhost or has sort of any number of sort of subdomains before localhost. And it's a big problem. This is a horrible problem. Because if you decide to test this, again, with something that's going to fail, we can absolutely see as people that testing this against that regular expression is going to fail immediately, or should fail immediately, because it doesn't end in localhost. But that's not what the engine does. The engine in this case looks at this first group at the start of the thing and goes, all right, cool, we can have anything 1 or more times. Let's do that. Let's grab all the anythings 1 or more times. We can go all the way to the end, actually. And then it steps back. It goes, okay, I do need a dot. I need a period after that. So it steps back 1 and goes, okay, we've got the last period, and then before that it was anything. And then this fails because we got an A at the end, not localhost. Cool. So we obviously have to look back at things. But that anything one or more times is very greedy. So it's going to look back and it's going to step back one and say, all right, cool, not that last dot. And then it's an A, so actually that's not a dot. So we have to look back again and we get a dot. So we get this one where we kind of go anything followed by a dot is that first group. And then we've got a second anything followed by a dot. And then we've got A, which fails it. But this just starts to build up. We step back again. We've got anything followed by a dot, and then another sort of anything followed by a dot, and then an A. And then that breaks up into two different bits that you can do it in. And that breaks up down to 3. And then the 3 kind of goes, oh, well, we've got 2 and 1, or we could do 1 and 2, or we can do 1, 1, 1. And as you can see, like every time we step back, we actually get more options out the other end. And so that is where it is turning into this exponential time problem, all in something that we can absolutely see is never going to pass. And this is actually really well illustrated in this one, the Regex debugger. We have this localhost URL and the string to test against, and if I test it, I get this debugger up, and this actually gives a nice kind of visualization in the middle of the way that it keeps going to the end and then having to check back and to the end and check back, and you actually have to speed it up because if our original regular backtracking issue had 22, 29, 37 steps. This one fails in 396 steps, even though it's only 14 characters long. As you see, it's got to around halfway there right now, and it's not quite dealt with the last 3 characters just yet. Speed up a bit more. That is as fast as it goes. Cool. This is Regex 101 and its debugger. It's absolutely great to debug your normal regular expressions when you're trying to fix something. But if you find that something's gone exponential, this debugger will show you all the steps it's trying to take to get through that. And it's really useful. Oops. And actually, I was going to do my little, I have this one set up in my timer thing as well. So this is testing this many A's against that thing, and my timer here tells me that takes 3.2 seconds to test and find a failure for this string of A's. But if that's 3.2 seconds, and we test it again by adding another one, we see that this next one is then going to take 3.4 seconds. Sometimes there's some caching that goes on in browsers. I'm going to guess that this one's going to get more close to 5 or 6 seconds. 4, 5, 6. Oh, yeah, okay, 6.8 seconds. And every time you add one extra .a, we can test it again, and it will almost double the time again. Looking for 12 seconds this time, 12, 14 seconds. Still going. I built in a stop button just in case you really go over. There you go, 12, 13, 13.6 seconds. So a seemingly simple regular expression like this, and a seemingly simple thing to test it against, can blow out into seconds worth of computation. And that's not good. I mean, the talk in this room just before was about dealing with everything in under 100 milliseconds. That was an entire ad serving thing. If your regular expression in somewhere in the pipeline there goes wrong, you've broken an entire business. So I want a real world scenario again for this one. So that happened in Node Fetch, but I don't know if it necessarily caused anybody's site to fall over. But Cloudflare, enormous CDN now powering a bunch of back-end stuff for people, did manage to have a bit of a flare up using a regular expression like this. And this is the big one. This is this regular expression. I think what this actually intends to do is a part of a series of tests that they did, which ran against pretty much all files going through their network, checking for injection attacks. Now, I'm not entirely sure what this is checking for, but that's supposedly what it was intended for. And it's confusing, it's difficult. And so actually, I definitely don't like dealing with 3 lines worth of regular expression ever. But what you can do with this kind of thing is visualize it. And there are a few visualizers out there on the internet. And this one's called Regex. You just put in your regular expression and it shows you kind of a breakdown of what it's actually doing. And actually makes it look a lot easier because we've only got we've got this 1, 2, 3, 4, 5, 6, 7 kind of things to deal with. And so this first one, on this side, that is all just an amount of 1 or more of certain characters, including, we've got star, we've got quotation mark, close square bracket, close curly bracket, slash, any digit. and then some JavaScript things like nan, infinity, true, false, null, undefined symbol, or math, then a couple of other little symbols, and it's one or more. So that all comes down to, we start it here, and it all goes to the end here. So it's that plus, one or more of them. And so that's all taken out by that one first part. Then we've got like this 0 or 1 of a closing bracket, 0 or 1 semicolon, and then we get this group here where we have another kind of 0 or more white space, or a dash, or an underscore, or an exclamation point, some brackets, 2 pipe operators, or a plus. And then here's the dangerous part. We've got this any character 0 or more times, any character 0 or more times, and equals, and then an any character 0 or more times. So we can break this down. We can actually make this a lot simpler by going, all right, let's take this first big column of things and just choose one from it, and imagine that has to be there. We need 1 or 0 or 1 of them. No, 1 or more of them. One of them will do. These 2 bits in the middle, these ones, they are 0 or more. Let's see that arrow that goes over the top of them, and that just says we can skip this, so we can skip it. And that first bit in the group as well, that has an arrow over the top that says we can skip this, we don't need this. So if we break it down from there, it actually turns out to a regular expression that looks a bit more like this. A quotation mark, and then anything 0 or more times, anything 0 or more times, and equals, and anything 0 or more times. And the real problem sits in that dot star, because there are multiple ways for that to match upon a string at the same time. Because it is anything 0 or more times, it can always just divide up the string in multiple different ways and match successfully. And ultimately, they deployed this and immediately took Cloudflare down for a 27-minute outage. And taking Cloudflare down is not just taking one website down. Although they did take their website down, they also took down a third of the internet with it. Because that's quite a significant CDN. And again, I imagine the person tasked with fixing this went to Google something and then went, well, no, Google probably have their own CDN, but I bet it probably affected Stack Overflow as well. And the fact that they actually couldn't look at their own dashboard, bit of a nightmare. They have a write-up on how they dealt with this as an outage, and it's very interesting to see that, because 27 minutes actually seems quite quick to me when you collapse a good portion of the internet, getting it back online in under half an hour with something, with a regular expression that looks like that, and you don't know at the start of that 27 minutes that was the problem. I think that's very, very amazing that they got that way, and the sort of communication and things. I highly recommend reading their kind of report on what actually happened. And then I just want to dig on this note even further into emails. Has anybody written a regular expression to match an email address? Yes, okay, a few. Bad idea though, right? It's a terrible idea. I mean, there is one published, I think, in like the email spec, which is about 3 pages long, and even the spec says this doesn't cover all of them. And so you should listen to it at that point and just be like, all right, cool. Well, I'm not going to mess with emails. This is a bad idea. But that hasn't stopped some people trying. Superhuman. Superhuman is an email application. It's an email inbox for built in Electron. So it's a desktop app, but its interface is built in JavaScript and HTML and CSS, a bit like VS Code or Slack. Superhuman, because they are an email inbox, obviously wanted to detect when emails were around. And they started sensibly. They went, okay, we don't have to do every email. It's not a good idea. This was their original regular expression for an email address. And what this says is, we have a bunch of stuff that is not an @ symbol, then an @ symbol, and then a bunch more stuff that is not an @ symbol. And that seems fair. It's an @ symbol in the middle, probably an email address. Of course, you can pass this regular expression, with an @ symbol and then some white space. Not an email address. But they were happy with that until they read the email spec. And they found out that you can have an @ symbol in the first part of an email, as long as it's surrounded by quotes, right? Bad idea. And they were like, well, let's handle that. Oh, we'll sling in this bit of regular expression at the start, which says, we'll either have a quotation mark, a bunch of stuff that's not a quotation mark, and then a quotation mark, or we'll have things that are not an @ symbol. And we'll do that 0 or more times. It was a bad idea. You see, what that allows is there is an overlap between not an at symbol and a quotation mark. And so it allows the regular expression to be like, okay, this could be that or that. And if I drop out into this, yeah, okay. This is our superhuman one. So I've loaded up the expression. And then if we test it against a bunch of quotation marks, it takes quite a long time. 4.2 seconds. And if we add a quotation mark, it probably doubles it up. Because it's checking, it doesn't double it up because it needs 2 of them at a time. That's going to double it up. There is some caching that goes on in a browser. So that now that was 1.2 seconds, now 2.1 seconds. Let's add another one. Now we're going for 4 seconds probably. 3.4, there we go. And it's sort of almost doubling each time you add another quotation mark. And again, as a human, we can see that there's no at symbols in there at all, but the regular expression thing is going, well, it could be an at or it could be a question mark. And it's just trading off between those two things. And Superhuman found that happened, and it would slow down their interface or bring their interface to an absolute stop, which is a real shame. And then there's Zod. So this is back to open source libraries. Zod, if you haven't used it, is sort of a runtime type checker for JavaScript. It's trying to do TypeScript for JavaScript at the runtime, which is great. I like the idea, except it added a bunch of extra types. And one of those types is email. And so they went, it's time to write a regular expression to match an email address. And everyone else probably screamed, no, stop. But somebody did it. And this is a bit more complicated than the Superhuman one. But the issue is highlighted there in the yellow at the start. And our issue here is we've got this sort of A to Z, 0 to 9, underscore, plus, and dash. And this is also case insensitive. The I at the end says we can use underscore A's to Z as well. As you might be like, all email addresses aren't capitalized. What are you talking about? But yeah, so it's case insensitive, but it's A to Z, 0 to 9, underscore, plus, minus, 1 or more times. And then 0 or more dots, 0 or more periods, and then all of that 0 or more times. And the problem is, as I pointed out actually in the Cloudflare one as well, that like question mark, that 0 or 1 time for the dot can actually be just deemed as 0 times. Let's think 0 times. And then we end up with this pattern here where we have a group with a plus in it and then a star on the outside. And so that's saying this 1 or more times, the whole thing 0 or more times. And that, again, allows the engine to check the things in multiple different ways, check the same string in multiple different ways, much the same as that sort of node fetch thing meant that as you sort of backtrack through the thing, you're just building out the number of different permutations of the string that you can check against. And that failed. So those are some failures. Those are some Dependabot updates that people got. That was a whole, we've got to fix our application because it's slowing people's computers down. How do we fix them? Well, we first want to know what we're looking out for, right? We're looking out for these nested qualifiers, things that overlap or things that, nest. And so we're looking at overlapping disjunctions. If you have an or, if you have that sort of bar in the middle, and we've got A or A and B, A or AB, 1 or more times, then the regular expression engine can match the A, any number of A's, either with the left-hand side or the right-hand side. And when it does that, it explodes the number of ways it can look at it. Then we have consecutive patterns. Again, I mean, we should be wary of the star or plus operator anyway from what we saw at the first part of the talk. But when we combine it with kind of things that overlap, dot star, that dot could be anything. And then we add another dot star, which is also anything. Every single combination and permutation of a string can be checked in that way. And then it's always good to look for those hidden consecutive patterns where you are putting an optional thing in the middle. In this case, at the bottom, we've got this like optional equals 0 or 1 times. You can almost just ignore the optional ones, squish the thing back together, and you go, okay, now I've got an overlapping consecutive pattern like this at bad times. And so those are things we're looking to avoid. They are hard to spot when you have a 3-line regular expression, but we get to how to fix those in a bit. So how we refactor our nested qualifiers in node fetch. This is not how they did it, but this is how we could do it. That was our original problem, where we had anything and then a dot, 0 more times. And the fact that the dot lies within the anything means is the problem here. And so we can say anything that's not a dot, and then things that are a dot. And we lose the overlap, and it means that that dot has to take every single time. That's much safer. So we're just eliminating an overlap there. We're eliminating the fact that the dot is at the end by eliminating it from the pattern at the start. Same thing for superhuman. They tried to be clever, and I appreciate what they tried to do here, but they were, with their sort of a quotation mark, and then things that are not a quotation mark, and then a quotation mark, and then things that are not an at. But the problem is that that overlap is with the quotation mark and the at, and so the second part of this disjunction to avoid the overlap is to say things that are not an at or a quotation mark. And when we do that, the whole time problem falls apart again. In fact, we can actually look at that as an example, as I have it in the timer here. If we are to go into that and say, all right, not just an at, but the quotation mark, it now takes a millisecond to fail, whereas that was 7-8 seconds or so before. So just eliminating the overlap, I'm going to leave that to go. There are some nice things in regular expressions called atomic groups. They allow you to set up a group in a regular expression that doesn't backtrack. But they're not a feature in the JavaScript regular expression engine, sadly. But you can fake them. It turns out somebody very smart, a lot smarter and more involved in regular expressions than I, came up with a way of faking them. And so this is how you would use a fake atomic group to deal with node fetch. What you do is use this question mark equals here, which is the look around operator. It doesn't actually consume any of the characters, but if you turn it into, you take this look around operator, you turn it into a group, so it's also surrounded by brackets, and then use the /1 at the end, which sort of places it back on itself. That stops the regular expression engine from then looking backwards. And it immediately works. It's very clever. I'm going to go in and see if I can do that on the timer here as well. It's on my localhost version. And so we're going to go look around, end the group, and test that. And yeah, now it finishes the test false in a millisecond. And that was previously taking, a few seconds to deal with. That I don't have time to spend any more time explaining, but there's a great blog post on that and how it works. But that idea of kind of putting a thing in place and then putting it back at where it exists stops the engine looking backwards. And stopping the backtracking is actually our achievement here. I said in the first part, avoiding regular expressions is actually probably your helpful thing. And that's what node fetch actually ultimately did. You see, we had this expression that said, hey, if the host, either ends in localhost or has a bunch of subdomains, is either localhost or has a bunch of subdomains on localhost, you can test that in a different way. We can say, hey, is the URL host localhost? Or does it end in .localhost? And that is the same as we're looking for, or it functionally achieves the same without the explosion in amount of time it can take to get something that's wrong. And so that's what node fetch actually did. That's the fix that's running in it today. And then there's an option to use a different engine. This is not an option for you in the front end, of course, but if you are using Node or something on the back end, you can actually install, so Google wrote an engine called RE2, and it's an engine that avoids backtracking entirely. It works out regular expressions in different ways. Now, this means it doesn't exactly work the same as the existing regular expression engine that we're used to, but if it could help, it might exist. It may well help for you. There are Node bindings for RE2, and so that is something you can kind of install instead. Alternatively, like I said, there are other languages that also have different backtracking different regular expression engines, and I believe that Rust, for example, their engine also does not do backtracking, and doesn't have quite the same amount of power that the JavaScript engine does, but it doesn't fall foul to backtracking issues like this. Now, finally, like I said, if we throw up 3 lines of regular expression on the page, and I say, "Where's the issue?" that's kind of hard. And so there are a bunch of ways that you can use to help spot these. Some of which you can automate, some of which you can just play around with yourself. This is kind of a really useful thing. So Superhuman, when they found they'd introduced catastrophic backtracking into their application, then went on to a big deep dive onto how to find out that and wrote a website called regex.rip. I think I might have that up. Yeah, there it is. And so if you put in the Node.js one, for example, it can find some, if not all, of the issues. So this one has picked up, this is vulnerable to exponential backtracking, and it tells you why. Lovely. Really nice tool. None of these tools are necessarily 100%, but they're better than nothing. Let's go back. Recheck is a similar tool. There is a playground online, but also you can actually implement it into your application as well. That's actually in the next down here. So ESLint plugin ReDoS, if you are using ESLint, uses recheck, which is a very good method for that, and was actually used to find the error in Zod. And so you can use that ESLint plugin. There's ESLint plugin Regex, which does a different set of things. And honestly, if you want to cover as much as you can, you might as well use both, although it might make your linting take longer. I used to work for Sonar, and SonarCube, as part of its security checks, will also check your regular expressions and see if it thinks they're fine. And so that's a useful thing. And then finally, like, you can go and use my little regex timer. I think that's a bit more useful to kind of just explore how these things blow out, and it's just a nice thing to play with, but that is up online on GitHub as well. And so that's all I've got for you. Regular expressions can be dangerous, and it's good to be informed that both those overlapping things or using stars at the end, the star thing or the plus quantifier, can allow for quadratic or even exponential backtracking for testing against strings that absolutely should fail, and you can tell that when you look at it. These regular expression issues have taken down some of the bigger sites and some of the parts of the internet that we know and use and love every day. And so they're easy to fall foul of. But now that you know, hopefully you are a bit safer in that knowledge and know that there are tools that you can use and ways to fix this to avoid this in the future. So again, my name is Phil Nash. I'm a developer experience engineer for DataStax, and it's been an absolute pleasure talking to you. Thank you so much.